questions on any of that? All right, cool. Oh, I about ended our meeting. It's a break. We're good. All right. Not that though, because I like you guys too much and the highlight of my week. All right. Okay. So we finished off last time going through a screening for this marital satisfaction data. Okay. So again, the idea behind this example is we want to know, or our hypothesis is that for individuals exposed to with accident-related PTSD, we're expecting differences in relationship satisfaction across men and women. But what we're also going to do is we're going to go through and test socially desirable responding to see if we were to see any difference, if maybe it would be a function of social desirability, right? So what we've done is we've got a small sample of individuals who've gone through who all have accident-related PTSD, and we're measuring marital satisfaction and Marlowe-Crown scores. Okay. Oops. And then what we had done is we went through our screening just to kind of bring you back to where we were at before. Is we went through, found one case, which happened to be a woman in our data. We removed that person, given that they were missing marital satisfaction and Marlowe-Crown scores, so we got rid of those. All of our range for Marlowe-Crown and Locke-Wallace were within acceptable bounds, so we're good there. Would probably on this just make a note that we removed one person and sort of indicating that we have a final sample of 26. Okay. Then we went through and we looked at distributions for our two outcome variables separately in men and women. Why did we do this, Robert?
Wait, so are you asking why we looked at them separately?
Yeah.
I don't exactly remember. I do know that there was a larger amount of females than.
Okay.
But I can't remember.
Yep. So we had 21 women, 5 men. Okay. But for this test, why is it important to look at our distributions of our scores separately in men and women?
I don't remember for this specific example.
Okay. Well, it's not just this example. We would do it for lots of different examples. Someone help us out. Why is it for an independent sample t-test to look at scores separately in our two groups?
Doesn't that just have to do with the nature of the question we're asking?
Yeah. Yeah, getting at that, right? So, let's say, Rachel, I've got a score that is really kind of way out there for men. Does that necessarily mean it's going to be way out there for women? No, right? I'm looking at two different populations, right? I'm assuming that sort of for my study, I've got population of male survivors, population of female survivors. So you got men and women. These are two separate populations for my study, right? And so what I want to do is I have assumptions about equality of variance, distributions. And so what I need to go through, and always for my independent samples test, is make sure I'm separating these out and looking at these two groups differently because they're different populations, right? I might find that my sample, my distributions are looking pretty good for one group, really kind of bad for another group. So always want to make sure that we're separating this out, okay? And so we went through, separated it out, found that our distribution for our men looked pretty garbage. But why was that, Erica? Do you remember?
Is it because of the small sample size?
Yeah, we only have 5 people. You're never going to get a nice looking distribution with only 5 people, right? So again, this is where context starts to come in. Our general rule of thumb-ish, where we start to say, oh, we might start to get into or drifting towards more concerning deviations from normality in our samples when you like skew and kurtosis greater than 2. Again, use that very, very, very loosely, but and so if I wasn't thinking clearly, I was like, oh, this is a terrible thing. But if I actually look at the context, I've only got 5 people, so I'm probably not too concerned about that, right? Among our women, they were looking pretty good, not too bad. A little bit of negative skew, negative kurtosis, but sort of nothing too interesting or concerning going on there. And then we looked at outliers. Remember, we made sure that we split our file before calculating those z-scores, right? When we're looking at extreme values, again, what we want to do is make sure that my z-score for my group is normed within sort of the mean and standard deviation of my group, not sort of everybody, so making sure that those are separate. And again, when you're looking at your screening output, if your mean and standard deviation for your z-scores isn't 0 and 1, when you run a descriptives on that, you know something's kind of gotten turned around, so make sure to take a look there. And then we've got this homogeneity variance test. We're going to talk about this in a moment. Our Levine's test here is going to fail to provide evidence for violation of homogeneity of variance, but we got a marginal effect for our Marlowe crown. So we'll see what that looks like and talk about sort of implications there. Okay. So then here in your summary, this is where you're just kind of pulling everything together, talking about stuff in order to kind of give your assessment of what's going on, what to be thinking about, sort of whether or not it's something to be concerned with, and maybe recommendations for moving forward. This is where you get to play consultant. Okay. All right. Questions about the screening?
So when we do this on the problem set, I'm just looking at it now. Is this what you want us to turn in? Something like this?
Yep. For any of those problems that has you going through screening data, go through and sort of use this format, bullet it out. It just makes it a lot easier for CJ and I to go. At one point early in our history with this, sort of like we would get like a page of text and it's hard to figure out what's going on. Use this structure, go through, bullet it. At the end, kind of just tie everything together with this summary. There's not many things I give you as a template to say, hey, follow this. This is a template. Follow this. Like, don't cut and paste my language. I mean, you gotta, and it's gonna change depending on the screening. You know, play around with stuff, describe it however you want. But in terms of the structure and the bullets and stuff like that, just it'll make your life easier. It'll make our life easier. We'll all come away happier for it. So we'll just have that as our plan. Okay. All right. Any other questions about the screening process? All right, cool. So what we're going to do then is, so this is a set I've gone through, and I'm going to move you out here. Just give me a little bit more space. All right, so what we want to do now, we've gone through, screened, and our biggest concerns really for this is going to be our unbalanced and our really small sample. Everything else is probably fine, but that's the biggest thing we're probably concerned about in terms of limitations of these data from an analysis standpoint. But what we want to do now is we're going to go through and actually run our tests. This is simple and easy and super fast. Okay, so we're going to go to Analysis, Compare Means, Independent Sample t-test. We click this. Here we go. Reset. Open this up. What I'm going to do under my test variables, I'm going to find my outcomes that I'm interested in. So I'm interested in my Locke-Wallace and my Marlowe crown. Okay, those are my 2 DVs that I'm interested in, and my grouping variable. Ari, what's my grouping variable here? Yep, you're going to look at men and women here. So I'm going to go through and I'm going to drop grouping variable into my, or gender into my grouping variable, but then you'll see there's these couple of question marks here, right? This is just because we're an independent sample t-test, we have to define what levels that we're wanting to compare. I could have some, let's say, a condition variable where it's got 1, 2, 3, 4 conditions, right? I only want to compare 2. It's an independent sample t-test. We can only compare 2. So we have to go down and we have to hit combine groups. All right. And what are the 2 values, Allie, that I have coded for gender?
Was it 1 and 2?
Yep, 1 and 2. Okay. This is an old set. If you've got dichotomous indicators, I would 0, 1 is a better way to do this. It'll help you down the road. But here it doesn't matter. It's just what are the 2 groups you want to take a look at. So my groups are coded 1 and 2. I'm going to hit continue there, and then I'm going to hit paste. All right. This is just going to save this into my syntax file. And again, I can say test of Locke-Wallace marital satisfaction scale and Marlowe-Crown social desirability. Okay, just tell me what I'm doing here. All right, you can go through. I'm going to run this, and here's my output. Okay, so up here, what we've got is just our descriptive statistics. Okay, this isn't going to be new information to you because you spent a whole bunch of time going through and screening your data to make sure that you don't have problematic violations of assumptions and all of that, right? But you always want to go through and take a look at this just to make sure everything checks out. Sometimes we go through and we run our screening, like things are looking good, but then something happens and the people we want in our set aren't in our set. Always go through and take a look at this. Okay, and so, yeah, Riley, looking at these group statistics, you seeing anything of note here?
I mean, the standard deviations for the Locke-Wallace are pretty big.
Mm-hmm.
The standard error for females on the other one is really small.
Yeah.
Comparatively.
Why? Yeah, that's not something that I would have drawn attention to, but I think it's good. Why is our standard errors smaller comparatively smaller for our women in on both of these?
I mean, just because they have a larger sample
size? Yeah, fantastic. I do. Big COVID-free hugs through the. Yeah, you're exactly right. Yeah, we've just got standard errors determined almost entirely by our sample size, and we got way more. 20 is still a small sample, but it's a lot more than 5, right? So we're seeing much smaller standard errors there, right? Would you be willing to sort of bet a large sum of money that we're going to find differences in social desirability here? Yeah, okay. So this is just a good thing to go through and do. Take a look at your descriptives. And that way, if you start to get things that don't line up, you start to flag stuff. You're back, okay, wait a minute. Like, so if we found like a massive effect, if I calculated a D of 1.5 for my Marlowe-Crown stuff, I would be like, oh, wait a minute. I need to go back through and check that. That seems not consistent. Or, there's not as many people in this one group as I thought, or there should be. Always go through and take a look at your descriptives to just make sure everything's kind of fitting together. Okay. So, what we're going to go down through, this is looking okay. Then we're going to jump down into our t-test table. This is pretty easy and straightforward. So we're going to start with our marital satisfaction scale. This was what we were primarily interested in. First thing we see here is our Levine's test for equality of variances, right? And remember, for our independent sample t-test, an underlying assumption of the analyses is that the populations from which our sample were drawn have equal levels of variance. So like they can have different means, right? But we're assuming that their variability is equal in men and women, all right? And with our Levine's test, what our Levine's test did, we talked about that a little bit about how this is calculated. Do we want to reject the null with Levine's, or do we not want to reject the null? What do you think, Allie?
We don't.
Yeah, we don't. Why?
Because we are hoping that the variance is about equal.
Right, exactly, right? So this is one of these where we don't want a small p-value, right? We're hoping that our data doesn't give us, and again, it's not telling us that they for sure have equal variances, because that would be accepting the null and interpreting the null as meaning that there's no difference. But what we can say is that our Levine's test is at least telling us that we don't have strong evidence for differences in our assumed population variance. And so, Allie, do we have based on our Levine's test here, do we have a violation of our homogeneity variance assumption?
No.
No.
For the Lock-Wallace.
For the Lock-Wallace. Yeah. So, good. So we don't have anything here that's going to assume that we have problems with homogeneity, or that homogeneity of variance is a big concern. Now, $1 million question. What's one thing that might give us pause with this Levine's test from a method standpoint? In this data set, is this going to be a powerful test? Brittany, you're shaking your head no. Why would you say that?
Maybe because your sample isn't large.
Exactly, right? This is the thing. Always, always, always remember what these tests are doing. They're not magical, right? What we've done is we have a test to see whether or not, trying to get evidence, trying to get a signal. Do we have any suggestion in these data that these scores have very different variances in their respective populations, right? We only have 26 people in our sample. We got 21 women and 5 men. If the goal of this test is to identify evidence of a difference, do we have much power to detect a difference? Nope, right? And so we're not going to get too concerned or worked up about this, right? But we should know that probably even if there were differences in the variance of these across these two populations, with 26 people, our Levine's test probably isn't doing a whole lot to detect those, even if they are there. Okay, but let's flip this around. What happens if I had 200 people, 200 women and 300 men? What happens to my test then? What do you think, Natalie?
Has more power.
Yeah.
Has a greater sample size.
Yeah, and not just more power. How much power? A whole lot of power.
Okay, I was gonna say
a lot of power, right? And so with a test that has a ton of powers, maybe overpowered like that, do we necessarily need to get too worked up about if our Levine's test gave us a small p-value? Maybe not. I don't know, right? Because remember, all that these tests are doing is telling us whether we have evidence that something is not zero. Okay, and so again, this happens too with indices of skew and kurtosis, right? Someone will have, I see this all the time. Someone will say, "Oh, I have significant skew," right? Okay, with p less than 0.001. You say, "Okay, well, you've got 500 people in your sample. What's your actual skew index?" It's 0.1. Okay, well, then you don't need to transform a bunch of goddamn stuff, because it's just saying you just have enough people in your sample to say that your skew isn't exactly zero. But that's not an assumption in your test. The assumption of the test isn't that skew is exactly zero. It's just problematic violations of normality, right? And so with this stuff, we start to it's important to take this into context, okay? So Erica, if we go down through and take a look, and jump ahead here to the Levine's test for Marlowe Crown. What are we seeing down here?
It's a lot larger.
Yeah, so our F value is larger, and this is not below that 0.05 level that we usually use as a threshold for interpretation, but it's getting kind of close, right? And so again, if I'm seeing that type of what we sometimes will call marginal p-values with only 26 people, might I have more concern that maybe I have unequal variance in my Marlowe Crown or my social desirability scores? Yeah, probably, right? Again, if I'm just thinking about this in terms of yes/no decision making, is this number above 0.05 or not above 0.05? I would say, well, for neither of these, do I have to worry about violations of homogeneity of variance. But I also know that I'm working with a very, very small sample, and so I'm probably not concerned about this at all, but sort of recognizing the limitations of the test for a sample this size here, I might start to think, well, I don't know, I'm not 100% sure that we don't have different, that men and women don't have different levels of variability in terms of their social desirability. I'm just getting something that's starting to eke closer to a small p-value, even with 26 folks. So just going to go through and take some of this stuff into consideration, okay? And it's just providing a nuanced interpretation based on what I know about the tests and how they work. Does that make sense to people? People kind of understand what we're up to? Okay, cool. So when we're going through and taking a look at this, if I don't have, or if there's very little evidence of a violation of my homogeneity of variance assumption, I can go through and interpret this equal variance is assumed row. If I do have evidence of a violation of homogeneity of variance, I would go through and I would look at equal variance is not assumed, and this is just going to be a corrected test statistic that is going to go back through, and again, we had talked about our Welch-Satterthwaite solution that's going through and sort of adjusting my degrees of freedom and my test statistic for potential violations. Okay, so you can see here I've got different t values, different degrees of freedom, different p values depending on, and confidence bounds and things like that, depending on whether or not I have a violation of homogeneity of variance or not. For this one, we're pretty safe to just interpret equal variance is not assumed, right? So we're going to take this top row. So we've got my t-test, this is my test statistic, my degrees of freedom, my p-value. This is just going to be my mean difference here, standard error of the difference, and then my upper and lower bounds for my confidence intervals. And so, Brittany, what might I start to think in terms of whether or not I have differences in social desirability across male and female survivors based on this sample?
Well, you said not to say significant, but it's significant for the Locke-Wallace stuff, right? Is that what we're talking about?
What does significant mean?
It means like, I hate my problem set. You said don't say that. So it means just like that there is evidence that there's a difference.
Beautiful, beautiful, right? That's much better. That tells me a lot more than saying that something's significant, right? Yeah, I mean, it just looks like based on these data, it's very, very flawed data, but based on these data, it looks like we may have some support for our hypotheses that men and women, male and female survivors differ to some degree in terms of their overall level of marital satisfaction. Okay? Just eyeballing that p-value, how strong is our evidence?
Pretty strong. I mean, you know, it's like, I would say it's kind of like 0.05.
Okay, so this is what we're going to do, and this is where just eyeballing that p-value, right? Yeah, we're less than our 0.05 criteria that we use in often use in science to go through and interpret, but you know, again, if we go through, and this is where those S values and those base factors start to become helpful. If I go through here, let me do this. What's that?
I was just going to say, I have that. That thing is so useful. I know you're making a search for the problem set. It is so.
What's so useful?
In the base factor bound calculator.
Oh yeah. Did you where did you get one of those?
I made it.
You made it. Awesome. You're ahead of the game.
It took me a significant amount of hours, but
okay, that's all right. Okay. So if I go through and oops, here we go. If I double click on that p-value and just copy that into my, okay. So again, what this is telling me, if I calculate my S and my Bayes factor, right, based on my p-value here, Brittany, what's my S value?
4.9. Sorry, I have to go up in our PowerPoint. Not sorry. Have to go and look. Well, I understand the base factor bounds a little bit better, so I guess I'll jump. That's like 3 successive head trials of a coin, right? That you get heads.
Flipped them around. S.
Oh, okay.
Right? And remember, we round up. So we've got an S value of 5. And so what does that mean?
1 second. Let me find it. I'll have to find what the S values. 1 second. S values. Okay, here they are. Oh, so that's what you meant. That's the coin one. So evidence against them, all that. So it would be like 4, 5 heads in a row.
Okay. Right?
And that's a little suspicious.
That's a little suspicious, maybe, right? But if I go through and let's say we do this. If I go random.org and I go to integer generator, you got 100 integers, 0, 1.
Oh, wow.
Right? How many times am I going to get 5 heads in a row or 5 tails in a row? There's 1. There's 1. Right? So there's a couple in here, right? And so actually, if we go through and take a look, it's okay. It's evidence for. This is probably not overly strong, right? Again, if we go through and take a look at our base factor is 3.2. So we would say, assuming sort of equal likelihood of the alternate and the null, we would say that the data-based odds of our alternative hypotheses are about 3, a little over 3 times as likely as the null. But again, if we go back through and take a look at our interpretive benchmarks for Bayes factor, that's, what is it, 3.2, 3.24. It's all right, right? But you want to bet the farm on that? Probably not, right? So again, and this isn't to take a dump on our findings, right? But we're just wanting to be careful in terms of sort of what we're doing in terms of evaluating strength of evidence stuff. Okay, so we've got our confidence bounds. Rachel, do you want to give me a hand on interpreting my confidence interval here?
Sure. So it looks like you estimates that are compatible with your data and differences between males and females for the Lock-Wallace score range between 55 points and 2 points.
Yeah. What do you think about that range?
Yeah, that's gigantic.
That is gigantic, right? So our data are saying that, yeah, we have some evidence that there could be a difference in marital satisfaction across male and female survivors, right? And our best guess is about a 28, 29 point difference in Lock-Wallace scores. But our data support population values of anything between about a reduction in by 2.5 points to close to 55 points. That's massive, right? So Rachel, how precise is our estimates?
Not very precise.
Not very precise, right? There's a lot of play. We've got, as Brittany said, we have some evidence to suggest that, yeah, there is a difference, and a difference in the direction that we had predicted that perhaps men do show lower levels of marital satisfaction post-accident, but that could be anywhere from something that's trivial to something that's quite big, right? And so at the end of the day, our data are pretty ambiguous about this, right? Like, there's not much that we can tell. I mean, we can say, yeah, we have evidence for an effect, but the extent to which this is practically meaningful, it's hard to know, right? And why is this, Ari? Why is there so much uncertainty in these data?
Sorry, I have a
Could you repeat the
Yeah.
question?
So why is there so much uncertainty in these data? From a method standpoint, what's the biggest limitation to this study overall? Yeah, the sample size, right? I'm getting a signal, right? And it's actually a pretty big signal. If I'm finding if something's popping up with samples of this size, it's probably, at least in these data, pretty big. My only problem is I don't know if it's going to be consistently that big. It could be anything from super, super small to even bigger than what we've found, right? And so we can say that, yeah, we have some evidence that there could be a difference, but the magnitude of that difference and the extent to which it's important start to become less conclusive there. Okay. So as we switch down over the real quick, want to take a look, because this was our concern, right? We said, all right, well, maybe we find differences, but maybe those differences are just because men and women differ in terms of socially desirable responding. Robert, do we have evidence of differences in socially desirable responding across men and women based on these data? No, not really, right? I mean, our estimates are imprecise, right? But these means are kind of right on top of one another. Right now, we had talked about, I'm going to take this Levine's test with a grain of salt. It's a really small, and so the fact that this is starting to creep towards sort of what we would use as an cutoff for interpretation, I wouldn't 100% say, oh yeah, no one will ever have problems with violations of homogeneity of variance here, but really it doesn't matter which one of these rows that we interpret. Technically, we can interpret this one. Howell makes an argument that we should always be interpreting equal variance is not assumed, but convention says we would go through interpret equal variance is not assumed. Our p-value is 0.9 something, right? So that's huge. Our means are right on top of one another. My confidence bounds for the difference in social desirability scores across men and women go anywhere from a 4.5 unit increase in one direction to a 5-point decrease in the other direction. 0 is right dead center in the middle of that, right? And so based on these data, we don't have evidence to support or conclude or really even to suspect differences in social desirability across men and women right now. It's a small sample. We have to take that into account. But it looks as though, based on these data, that the difference that we are seeing across men and women in terms of social desirability isn't easily attributable in marital satisfaction, isn't easily attributable to social desirability, right? Could be due to other things, but social desirability doesn't appear to be a candidate here.
Right. Can I ask you a question?
Yeah.
When you report this 95% confidence interval, I'm looking a little bit ahead, do you include that it's negative? So so it says like negative 5.0, like 5.0. Do you report that as negative when you do it?
This is a good question. This comes up, right? In a case like this, do we care about does the sign matter in terms of the sign of our tests? Rather you're shaking your head. Why? And you're right. Why don't we? Why should we not be overly concerned with the sign here?
Well, I mean, I just interpreted the sign because it's talking about a change, right?
Mm-hmm.
So it's not really like saying that it's necessarily a negative number.
Oh, that makes sense.
Right. Okay. And I guess, how do we flip that sign around for our test statistic or for our confidence bounds? We just swap out whoever gets entered first, what group gets entered first in our calculations, right? Here, if we subtract men from women, we get a negative value for our test statistic. If we subtract women from men, we get a positive value for our test statistic. It doesn't matter. It doesn't change the statistic at all. We just need to be very clear in terms of which, sort of making sure we're interpreting properly in terms of sort of how we're doing this, right? What's that?
Sorry. Well, our mean doesn't, so when we're like interpreting this again, the mean that we use is the one that's up here, like the 80 and the 108, right? Not the mean difference thing, I guess, just throws me off. But I'm just trying to understand. Our mean doesn't fall within our confidence bounds, but that's okay.
Okay.
Just like always, right?
Okay. Yeah. No.
Okay.
This is another thing too. Should your mean fall within your confidence bound? Yes. Always.
No, okay, that's what I thought.
Okay. But what is Brittany? What is this confidence interval? What is this a confidence interval around?
Oh, the difference.
The difference.
The differences. Oh,
Yep.
okay.
Okay.
Okay, I see. Okay.
We've got a 2-sample test, right? So we've got men subtracted from women or women subtracted from men. Who cares? Doesn't really matter as long as we understand sort of what's going on, right? If we flip this around and took women and women's scores, subtracted it from men, we get a mean difference of 28.64381, which just says women are 28.6438 units higher with a lower bound of, this sorts around men. Women, our data would suggest that women are at minimum 2.5 points higher than men, all the way up to 54.6 or 8 higher than men, right? So all you need to do is make sure that you understand who's higher than who, making sure you're interpreting appropriately, and if you got that under control, you're going to have it made in the shade. Okay. All right. So questions about what we've done here. Pretty easy, and again, within my syntax file, if I wanted to go through and say run the same comparison for CAPS total, right? I just go through. CAPS is a continuous measure of PTSD symptom severity. If I go CAPS there and then run that, now it just gives me a test of whether or not I have differences in PTSD scores. So again, do take a look at your syntax file so you kind of understand how these are going. And once you do that, you can save yourself a lot of time in just modifying syntax that you have to make sure that you're going through and it's picking stuff up. Okay. All right. Let's kick back to here. All right. Bring you all back. Wonderful. All right. So our independent sample t-test and SPSS, again, this is just going down through, showing you where to go through and pull information from, your pull-down menus, your syntax. This is our output that we just went through and took a look at. Have our descriptive statistics, your Levine's test for homogeneity of variance. Again, we're hoping for large p-values here. We don't want evidence of differences because that would be an indicative violation of our assumption. Depending on the results of our Levine's, we've got our equal variance assumed or equal variance is not assumed, right? And then corresponding test statistics here. In Stata, Stata doesn't, you have to request your Levine's test in Stata for Robert and Ali, but it's pretty easy. You just type in robvar and then your outcome by whatever your grouping variable is, and then it'll just give you that, right? If you say the same thing, robvar MC by gender, gives you the same thing. It'll give you a number of different tests. This first one is your Levine's test. If you go through and take a look at that number relative to what SPSS gave you, it's the exact same thing, okay? So you're just going to go through and type in a command to get that separately. For your t-tests, pretty simple. T-test outcome by whatever your grouping variable is, and then depending on what this unequal specifier here, if you have evidence of a violation of homogeneity of variance, then you can just hit unequal and it's going to give you your corrected tests. If you leave unequal off, it's going to give you your regular tests. So you can just go through and specify whatever. So this is our test. Other thing we want to do is calculate our effect sizes. Okay. Erica, what type of effect size should we probably be calculating here for these data?
I forgot what they are.
Okay, and that's fine. Anybody? So if we're thinking, because remember we've got a lot of different options, right? We've got raw differences. We've got glasses delta. We've got hedges G. We've got unbiased G. Here I've gone through and calculated unbiased G. Why is that?
small samples.
Yeah, I got pretty small samples, right? My concern is that with really small samples tend to overestimate effect sizes. And so what I'm going to go through and I'm going to do is I'm going to just calculate unbiased G. Do we have a good case for Glass's delta here? Allie, you're shaking your head. No, why is that?
There's not like a control group or anything.
Yeah, I mean, who's my control group? Whose standard deviation do I base my test on? Right? There's no real good control group, so probably a pooled estimate is going to be better. And so, which would give us a hedged G, but we've got a small sample, so probably unbiased G is a better way to go. Again, what I've done here is just showing you kind of my handwork. Scores for Locke, Wallace, Marlowe, Crown. Here, we're calculating my pooled variance. Robert, why did I square these standard deviation values here?
Because we can only use variance in this situation.
Yep. If I go through and what I get, so here I've gone through and taken sample size -1 times what will be, take the square of my standard deviation, which will be the variance for men. Same thing over for women, divided by sample size for men, sample size for women -2. Run the math. This gives me my pooled variance. And then I can go through and then take the square root of that to get my pooled standard deviation, right? But if I go through and I take 4 times 30.366 and 20 times 24.415, add those, and then divide by 24, right? So I just ran this right here. I get I get a result for standard deviation, a weighted standard deviation of 25.407. Okay, it's close, but it's not right, because if if I'm doing this correctly, the square root of my pooled variance is not equal to the pooled standard deviation. Always be working with variance and then get backwards from there. Okay. So I went through and did this, then calculated my estimate for Hedges G, and then took my Hedges G, applied my correction statistic, and got down to my effect size here. Okay. Same thing, Marlowe Crown, went through, calculated my pooled variance, took the square root of that, got my pooled standard deviation, calculated Hedges G, then Hedges G times my correction factor. When we see it doesn't drop too much here. It dropped more here. It would be hard for this effect size to get much smaller than that. But again, we just wanting to be consistent across this. Quick word on calculations. Okay, as you're going through and calculating things, in your hand calculations, just try and carry things out to 3 decimals. You don't always have to report things to 3 decimals, but in your hand calculations, carrying them out to 3, that will just help save CJ some time in trying to figure out whether or not you've made an error, if it's just a rounding thing. So with these, I eventually am reporting my hedges or my effect sizes to 2 decimal places is fine for G. After that, it's just sort of random digits for the most part, right? But in the calculations, just trying to stay consistent with this. All right. Questions about the calculation of our effect sizes here? All right. Now, for those of you using Stata, nice thing you can do is if you go through and you type in eSize 2 sample, whatever your outcome is, by your grouping factor, and then you just specify all at the end, what it'll do is it'll give you a whole bunch of effect sizes along with confidence intervals around those effect sizes and just calculate it all for you. So Cohen's D is that's Hedges G. Okay, so the Cohen's D, it's just stated term for basically the formulas are going to be the same for Hedges G. Hedges G is actually Hedges unbiased G. So just make sure that you sort of know kind of where those are at. Okay.
Could we do that instead? Like use data instead of hand, or do you want to see it by hand too?
Well, for some of these you want to see it by hand, but
Okay.
yeah, I don't know. If you want to sort of work over and work in Stata, you can do that. That'd be awesome, because that's what you got in SPSS in terms of calculating your effect sizes and and confidence bounds. Brittany, I will have you go through and create another Excel calculator that goes through and calculates all your stuff based on means and standard deviations and stuff like that, so you don't need to worry about it. But for Allie and Robert, it's a nice way to double check your work to make sure that you're on point if you are doing things by hand. Or anybody else who wants to use Stata. I don't want to cause a revolution, but it's sort of a slick program for a lot of reasons. So, okay. So how do we go through and write this up? Again, for an assignment, this might be how I go through and pull things together. This is just me being comprehensive, right? So I'm saying independent sample t-test used to compare marital satisfaction, social desirability across male and female accident survivors diagnosed with PTSD. Null hypotheses tested deposits no difference in satisfaction or desirability across male and female survivors. This is just, you can ignore this. This is just kind of, if you go through and you write a screening, you don't have to rewrite a screening in here, but this is just, second paragraph here is just screening stuff. But then down here, we start to try and take, because we've calculated a lot of information. We've got test statistics, we've got confidence intervals, we've got S values, we've got base factors, we've got effect sizes. Think about how we integrate this all together into something that's meaningful, right? So here, and again, this is not the only way to do this, right? Like, sort of be creative, sort of tie this together, things that make sense. But we're saying that here in this example, Marlowe Crown scores failed to provide strong evidence for differences in social desirability across male and female survivors, right? So here's my mean standard deviation, mean difference, my confidence bounds. Independent sample t-test identifies observed data is generally compatible with null or near null differences in these populations, given the assumptions of the underlying model here, all right? Not much else to say, right? Like, this is so clearly not different, or sort of, they're very, very sort of functionally no evidence of differences here. We don't have to say talk a whole lot about this, right? But then we might say results do indicate potential for greater marital satisfaction in female survivors, with a point estimate of unbiased G suggesting a full standard deviation increase in scores among women, right, as compared to men, right? So again, I'm getting mean standard deviations, and G. So what, Rachel, where am I getting this suggesting a full standard deviation increase in marital satisfaction scores among women? Where am I getting that from?
Is that the effect size?
Yeah. Okay. This is just modeling what I want you all to be doing. So what we typically do, right, is we just say, oh, here's the effect size, and don't actually think about it. But actually our effect size, if we're going through and giving a meaningful interpretation, contains a lot of information, right? What we're saying is my unbiased G 1.09, okay? And so what I'm doing in terms of my interpretation is saying that based on our data is suggesting that women are scoring a full standard deviation higher than men with respect to marital satisfaction, right? Is a 1 standard deviation increase big? Yeah, it's noticeable, right? That's again, that's something I can see very clearly with you just see it, right? I don't have to do a test. It's very big and very obvious, right? So again, providing some context around that. We're saying confidence bounds, however, identify values ranging from 2.45 to 5.84 as plausible estimates for the true difference in mean satisfaction across populations. It's worth noting that lower bound estimates supported by these data are likely not consistent with meaningful differences given observed variability in Lock-Wallace scores. Okay, so remember, if we go through and take a look at my Lock-Wallace scores range from 2 to 158, right? And so if the actual population difference is the minimum supported by these data, about 2.5 points, Is 2.5 points likely a meaningful difference in scores? Probably not, right? What I did is I just took 2.45 and divided by the standard deviation for men and women, so somewhere about, independent sample t-test also provides only modest evidence for an absolute difference in marital satisfaction in the larger population. Here I've got my test statistic, my p-value, my S, my Bayes factor. Bayes factor with these data suggests likelihood of alternative hypotheses is at most 3.3 times that of no difference, right? Odds correspond to 23.6% chance of the null hypothesis being true under optimal circumstances, right? So again, this is just taking that Bayes factor and changing it over into odds, or excuse me, a percentage likelihood of the null, right? And so again, if I'm saying, hey, there's a 23.6% chance of something happening, is that a rare thing? No, that'll happen a fair amount of time, right? I wouldn't want to put too much on that, right? So again, just trying to put this into context. The small and unbalanced sample further limits inferences that can be drawn. Although these data suggest the possibility of greater marital satisfaction among women as compared to men, strong conclusions regarding the magnitude and generalizability of the discrepancy require further study. Okay, so again, just trying to take this together and put it into a thoughtful thing, right? So if you're thinking about your interpretations, once again, think about yourself in the role of consultant, right? Someone's asked you to do this, right? And they want straight talk. So what can I infer from this? You're saying, okay, well, it looks like, yeah, we have some evidence of a difference, but we need to be careful in how strong we want to say that, yeah, this is really something that's going on with this. Okay. Questions about the write-up, kind of how I sort of put this together, structured all this up?
So just looking at the problem set, so for the ones that include the SPSS stuff, the interpretation should be something like this, like go through, use SPSS, and then like what I'm trying to get at is for like the questions, that we did by hand, do you still want us to do those by hand? So like I'm just looking at it and it says like calculate a 95% confidence interval and the effect size. You want us to do that part by hand, not in SPSS?
No. Like, if you have SPSS data, use SPSS. Right? That's what you have those tools for. I mean, some things like your effect sizes, your Bayes factors, like SPSS won't give those to you, so you have to calculate those on your own. But unless I explicitly say, hey, do this by hand, just let SPSS do it for you.
Okay, sounds good.
Okay. All right. Now this is way too much to put into probably a pub. Here might be something that's a little bit more streamlined that you could sort of put in for a publication, right? Sort of pulling this stuff together. But sort of for this class, for what you're doing, I want you to talk about things to demonstrate that you have a good understanding of kind of what these statistics mean, how they all come together. So just make sure that you're elaborating appropriately. You don't have to go pages and pages and pages, but sort of make sure that you're talking about things and implications for upper and lower bounds for your point estimate, sort of levels of precision, as strength of evidence, sort of effect sizes, kind of tying that all together to show that hey, I know what's going on with this. Okay. All right. Questions? Cool. All right. Let's take a break. Let's come back at 3:30, take 10, 3:30, and we'll jump into paired sample test, repeated measures. I love repeated measures. Repeated measures should be your best friend. So we'll catch you in 10. All right. All right. How are we feeling about independent sample t-tests? Riley, reading your signals loud and clear here. It's good general advice, right? It's just have that hanging out on windows and stuff like that, Okay. Feeling okay with independent sample tests or single sample tests and independent sample tests, right? How we're going through and starting to take and weave together confidence bounds and test statistics and effect sizes and things together. Feeling okay? Okay, cool. All right. Let's get into last part of our trifecta here in terms of our means-based tests. Okay, our repeated measures. Okay, think about a repeated measures designs as starting to work a little bit more efficiently with the resources that we have. Okay, if I'm talking about a repeated measures design, what I'm doing is I've got the same group of participants, and I'm going through and I'm measuring those individuals on one or more variables across 2 or more occasions. So I've got one sample, and I'm just measuring on them a couple different things, or it's in one different thing, sort of 1, 2, 3 times, or at least 2 different times. Okay. Now you see I've got an asterisk up here. This is just to note that if we're going through, has anybody ever done any work or had any exposure to matched designs? Okay. If I've got a matched design, what I do is I have group A, so that have been selected for this reason, and then what I've done is I've got a control group that's matched on a bunch of different characteristics to sort of try and keep everything equal. In this situation with matched designs, historically, the classic approach is to treat matched designs as a within subjects test, but generally for our repeated measures, what we're doing is we're looking at this with the same set of individuals measured on multiple occasions, right? Benefits of our repeated measures designs, a lot of the stuff that we're interested in looking at start to fall into line with these types of repeated measures approaches, right? I want to see whether or not I'm learning something, if learning outcomes have increased, or if psychopathology is decreased, or my performance has changed based on sort of one thing or another. So repeated measure designs are intuitive for a lot of the questions that we have. A much more efficient use of our resources. So I want to go through, and if I can, just take the same group of people and measure them on a couple of different occasions. That's a much easier way to go about things than having to get a new set of people every single time I want to go through and make an assessment. And the biggest, I think, benefit here is our ability to control for random error. Okay, if I go through and I've got Robert, and I'm measuring Robert on some outcome each week, Robert's outcomes at each week, they're going to be more consistent and less variable than 2 individuals measured separately. And if we can start to pull out that random error or account for that, if Robert can serve as his own control across multiple assessment points, what that ends up is it ends up being a much more powerful test. Okay, and we'll get into a little bit of the math on sort of why that pans out. Right? And our simplest repeated measures design is going to be our paired sample t-test. With our paired sample t-test, what we're going to do is we're going to look at change in scores within individuals across repeated assessments. Okay, and this is very important, right? When we're talking about our paired sample test, our difference scores. The difference between time 1 and time 2, this is our primary unit of analysis. Okay, what we're going to be doing here is basically a one sample t-test. We're just looking at difference scores. Okay, so scores at time 1, scores at time 2, fine, whatever. We really don't care about those. All we're interested in terms of the analysis aspect of things is just that difference score. Okay, so for our paired sample t, okay, our null hypothesis is the mean of the difference scores is equal to 0. Okay, if the mean of the difference scores is equal to 0, that means on average there hasn't been any change. Some people have increased, some people have decreased, but on average our score is 0, no change. Our alternative hypothesis is that the mean of the difference scores is some non-zero value. I don't know, right? My test doesn't tell me if it's meaningful or practically relevant. It just says that whatever the difference scores are, they're not 0. Okay, and if we're thinking about this from a diagram standpoint, we can say, all right, I've got some population. I want to know what the population difference score is. If I took all individuals in the U.S. and I had them some sort of executive functioning test. And hypothetically, I took all residents of the U.S., measured them first on executive functioning, and then measured them again on executive functioning after they did, I don't know, Ari, I know Meredith does this stuff, what, like brain games or some sort of brain training stuff, sort of like use this app and it's going to improve your executive functioning. Well, let's have everybody measure executive functioning before, measure executive function after, and see what the population difference score is. Do we see change, right? We obviously don't have access to the population, but what we can do is we can run a sample and have them measure before, have them run the intervention, run them after, and see if there's a difference there. Okay. So again, the key question here is, do difference scores across multiple assessments change sufficiently from 0 in order to conclude some non-zero difference in the population? Are the deviation scores, are the difference scores I'm seeing in my sample big enough for me to conclude that, yeah, there's likely some sort of change or difference in the larger population based on the data that we've collected? People see what we're doing here, how this is a little bit different? Okay. So our data for our paired sample data, our t-test is just going to be the mean difference minus the population difference assumed under the null over the standard error of the mean difference. Okay, and our standard error of the mean difference is just going to be the standard deviation of our difference scores over the square root of our sample size. Okay, does this look familiar to anybody? What are we working? Where have we seen a formula very specific or very similar to this previously? Any ideas?
Is it an independent sample t-test?
Okay, not an independent.
It's one of the t-tests, though, right?
What is?
It's not independent, it's single.
Single sample t-test. Yeah, yeah, very similar to a single sample t-test. And all we're doing here is in this small set, right? What we're doing is we've got, let's say, participants A, B, C, and D. We measured them at time 1. We measured them at time 2. And then what we're going to do is we're going to subtract time 2 minus time 1. When you're doing paired sample tests, always subtract time 2 from time 1. It doesn't impact the actual absolute value of your test statistic. It'll just give you the sign that sort of corresponds to increase or decrease. So here, for person A, our score went from 5 to 9. That's a 4-point increase. 6 to 13, 7-point increase. 7 to 12, 5-point increase. 9 to 7, 2-point decrease. If we subtract time 2 from time 1, it's just the sign is just going to be easily interpretable in terms of proper direction, in terms of increase or decrease. Okay, so what we've got at the end is that we've got a set of difference scores, and these difference scores have a mean and a standard deviation. This is what we're going to use in terms of our actually calculating our test. Okay, and so our question with our paired sample test is going to be, what's the probability of obtaining a set of difference scores with a mean of 3.5, assuming that the null hypothesis is true? Okay. Zerica, what's the assumed value for the population? What's the assumed value of difference scores under our null hypothesis? 0, right? So this just goes away, and our test statistic is just the mean of our difference scores over the standard the standard error of the difference scores. Standard error of the difference scores is again just the standard deviation of the difference scores over square root of our sample size. Okay, and again, this should look familiar because it's just our single sample t-test, right? We're just running a single sample t-test on our difference scores with our reference value being 0. Under the null, we're assuming no difference, right? And so again, very simple. It's the same exact thing that we've done in the past. Time 1 can be whatever, time 2 can be whatever. We really don't care. What we're really interested in is this column of difference scores. Questions about this? All right. So assumptions of our paired sample test. Formal assumptions, we assume, once again, because it's a t-test, that our outcome variable is continuous. We play around with this a little bit. You know, we use ordered Likert scales and pretend they're working, they're actually continuous scores, and that works probably okay most of the time. We're assuming the sampling distribution of different scores in the population is normal. Okay, so once again, Robert, do we care about the actual observed, the distribution of the observed scores? Is the distribution of the observed scores technically part of my assumptions?
No.
No. Right? I'm interested in the distribution of the sampling distribution. And under what two conditions does the sampling distribution start to become normal very quickly?
As this. Oh.
Yep, go for it.
Me, right?
Yeah.
Hello, internet. Okay, yeah. So if the sample size increases and if the population distribution is normal.
Right. So if the distribution of different scores in the population is normal, or if I start to get reasonably large sample sizes, right, that distribution of sample means starts to become very normal very quickly. But what we want to do is we want to go through and just know kind of how our data are distributed in order to facilitate inferences, right? Informal, we're assuming that we don't have extreme values that are going to start dragging things around. And then all our auxiliary hypotheses that we've talked about before, right? All the stuff that's going on in the background that we typically aren't thinking about, but we absolutely should. Again, these tests were developed based on mathematical and statistical theory. If these things are true, then the probabilities are 100% accurate. But particularly in psychological science, our samples are rarely, if ever, representative. Our samples are never randomly selected because we can't randomly compel people to do things, right? So again, all these auxiliary hypotheses. So when you're seeing in my example write-ups, right, when I'm talking about these qualifiers, I'm saying, assuming sort of some underlying assumptions of the model and auxiliary hypotheses are reasonable, that's sort of this stuff. If they're not, then we start to lose confidence, right? All right. So this is our test statistic. Our paired sample TR effect sizes. Okay, so a couple things to be thinking about here in terms of effect sizes. Again, mean difference scores are if we have some outcome that has some sort of meaning, just raw differences can be effective, right? So no one right now is sort of working in Kyle's lab, but if I was in Kyle's lab and I wanted to say I was looking with folks who have difficulty with eating pathology, and I say, okay, this intervention helps people sort of increase X number of pounds who struggle from restriction or something like that, right? I know, let's say it's 10 pounds. I know how much 10 pounds is. I know how much 10 pounds is relative to human beings, right? And so I can make a decision back, oh, that seems like it's probably pretty meaningful, right? If I've got an intervention and sort of pre-post, I'm seeing something that's, so I have evidence of a change, but that change is, say, like 0.2 pounds. I might not think that's super meaningful in terms of practical impacts, right? So if we're working with metrics that have intrinsic meaning, we can go through and take a look at raw difference. We can also calculate a Cohen's d, right? Cohen's d is, again, the mean of the difference score over some standard deviation, some metric of standard deviation. What's Allie? What's wrong with what's ambiguous about just straight up Cohen's d here?
It's tough with I think t-test because you're comparing two different groups, so you have two different standard deviations.
Okay, so with our paired sample test, are we comparing two different groups?
Well, yeah, time 1 and time 2.
Okay. So it's just one group, but two different time points, right? And so you're right. Which time point do we use? Do we use baseline? Do we use 1? Cohen doesn't tell us. He just has standard deviation, right? And so what we can do is we can go through and we can standardize our effect using the square root of the average variance, okay? So once again, note that your average, the square root of your, for your paired sample test, your the square root of your average variance is going to be equal to your pooled variance. Okay. So for a paired sample test, why can I just take the average of the variances? Why don't I have to work through that pooled formula?
Your sample is the same size because it's the same people.
Exactly. Perfect, Brittany. Your sample is the same size. So if we're looking at Cohen's D here using the square root of our average variance, we don't have to pool because I got the same people. It's the same sample size. I mean, I can run it through the pooled variance formula. It's just quicker to do this. Okay. The one thing to note, though, is that the square root of your average variance is not the same thing as your average standard deviation. Those aren't equal to one another. So again, always remember that when we're using these, that we need to be working starting with our variance, take the average of the variance, and then take the square root of that. In SPSS is just going to give you standard deviations. What you'll feel compelled to do or try to do is just take the average of the standard deviations. Don't do that. You're going to be off. You need to take the variances, take the average of that, and then take the square root. Okay. So this is Cohen's Z. That's pretty straightforward. Glasses delta. And Glasses delta is nice for paired sample tests because oftentimes that first time point is a baseline, right? A lot of the times it's like, okay, we measured people pre-intervention or pre-manipulation, and this is the variability that we see and understand just in sort of the normal world. Then we go through and we apply some sort of intervention or manipulation and then measure people on the back end. Well, a lot of times it's just easier and more intuitive to say we're seeing X standard deviation units and change relative to baseline variability or something along those lines, right? So Glasses delta is often sort of a nice way to go about this. Okay. Other thing we can do, and this if you're doing secondary analyses from published data, you can calculate an R-squared value based on the test statistic. You take your t-test, your actual test statistic, square that divided by the square of the test statistic plus your degrees of freedom will give you an R-squared value. Don't use this for the stuff that we're doing because your R-squared values, it's a measure of association. It's hard to, for a group-based test, it's just easier to report things and so more intuitive to talk about standard deviation, increase, decrease, things along these lines. Okay. So these are some options, but we also have a couple other options here. Okay. One thing that you'll see people calculating is using D and using the standard deviation of the different scores as your standardizer. Okay. We'll use this metric for certain purposes in sort of the next lecture, but the problem is, and Hal talks about this, is what can happen in certain circumstances if you're using sort of what I've got labeled as D-diff right here. A couple of things. One, the standard deviation of the difference score starts to become hard to interpret in terms of this is the standard deviation of different scores across time 1 and time 2. It's hard to kind of think about that in terms of variability. But the other thing that can happen is this standard deviation of the difference score can start being much, much smaller than standard deviation at time 1, standard deviation at time 2 that would go into the average. Okay, so let's say that I'm all of you are helping me out with a paired sample test, right? And so I measure you all at the start of the semester, and you folks are all over the place, right? So Allie's got a score of 5, and Natalie's got a score of 110, and Ari's got a score of 98, and Rachel's down at 3. Robert's somewhere in the middle in 50. Huge, massive variability, right? And then at the end of the semester, I measure you all again, right? And what we see is, again, massive variability. Ari and Natalie are still way up at the top. Robert's down at the bottom. Robert's in the middle. Allie's at the bottom. America's in the middle with stuff too, right? But what I find, even though at time 1 and time 2, you have huge variability in scores, but you're all changing about in the same way. All of you change about, say, 7 to 8 points, okay? So, Riley, at time 1, what's my variability look like?
There's a lot.
There's a lot. In time 2, what's my variability look like?
Also a lot.
Also a lot. And if I take the average of a lot and a lot, what do I get?
A lot.
A lot, right? But if you all are changing about the same, about 7 to 8 points, and I take a look at your difference score, what's the variability of your difference score is going to look like?
7 or 8 points, right?
Well,
Pretty small, right?
yeah, it's going to be very small, right? Because even though you all start and you all end in very different places, your level of change is 7 points, 8 points, 8 points, 7 points, 8 points, 7 points, 8 points, something like that. And so the amount of variability there is really small. And so what does that do to the estimate of my effect size if I use the standard deviation of different scores instead of the average of where you are at time 1 and time 2?
Me?
Yeah.
If you use the standard deviation, it would be bigger because that would be smaller.
Yeah, exactly. I'm using a much smaller number as my standardizer, and what can happen is this D value can be way much higher than what it would be if I was calculating it this way. And so Howell cautions the use of the standard deviation of different scores as a standardizer, because what can happen is that it makes your measure of effect look way bigger than what we would use calculating something like this, and can start to lead to misleading expectations about the magnitude of the difference. Now, we'll use this for power stuff, and there are reasons where we'll go through in terms of things where we'll use something like this, but be very careful. You'll also see this repeated measures D, where you take basically this number and divide it by 2 times 1 minus the absolute value, the correlation between time 1 and time 2. This will also inflate your scores. Again, this is important for calculating power, but doesn't produce anything that's reasonably interpretable or comparable to effect sizes that we would calculate from our between group samples. And so these are out there, but you want to be careful with using these because we lose interpretability, and we have some pretty strong concern that this could inflate the effect size. Okay. Now, for all you clinical folks out there, one of the things that'll happen is there's a possibility that D difference, by using the standard deviation of the difference scores, could inflate your effect size. But if we think about some types of things like intervention, right? So if, Robert, you go through and you have people who are in PTSD treatment, right? And so you have, say, 100 people go through, you're likely to see some people get way better, right? See huge reduction. So they got lots of change. And some people have like a little bit of change. Some people don't change at all. So for a lot of applications, we can see even the standard deviation of the different scores are huge, right? And the standard deviation of the different scores can sometimes even be bigger than the standard deviation at time 1 and time 2, right? And in that case, we're not super concerned that this metric is going to inflate anything much at all, right? But let's say, Erica, you're running like a lab-based manipulation where you have people coming in, and let's say it's an emotion prime or something like that, and it's pretty effective, and you're seeing everybody's kind of coming in at different levels, right? Some people are happy, some people are mad, so whatever. But based on your experimental manipulation, everybody's changing in the same direction and about the same level. What you can start to see is the standard deviation of the different source, standard deviation of the change is pretty tight relative to where people come in, and that's where we can start to have problems with this being a pretty large overestimation or inflation relative to what we see over here. Okay. People understand how we're going about calculating our effect sizes here for our paired sample tests? Okay. All right. So
I have one quick question.
Yes,
Sorry.
yes.
I didn't unmute it quick enough. Which one would you recommend, like, for most of the time when we're doing paired sample T, would you recommend, like, the modified Cohen's T normally, or does it still kind of...
Depends, right?
Depends.
It's going to depend, right? And so this is where, and I'm going to ask you to do this, right? To say, okay, so tell me sort of which measure of effect size you're going to use and tell me why, right? Probably, you're going to well, I don't know, with paired sample stuff, it's kind of a Wild West show out there. It's who knows, right? And if people say, oh, we calculated Cohen's D for this, which one? Like, what do you mean? What's your standardizer? That's always the key question here, right? And unless someone tells you, you don't know what they use as their standardizer, and I can't really interpret stuff because things could get funky, right? Oftentimes, if I've got a nice standard or a nice baseline, Glass's delta is really nice. It's super interpretable, right? But there's some stuff that we'll get into calculating confidence intervals around effect size. And if we get confidence intervals around effect size, so we're kind of back to using this for reasons we'll talk about down the road. But just want to think about taking into context, Natalie, so what my data look like and so what my design looks like and the purpose of what I'm trying to communicate, and then make a determination based on there. Cool. All right. So we're going to do our last example here on some issues with anger imagery. So here we've got researchers interested in the impact of mental imagery on the regulation of subjective anger. Pilot study conducted to determine the efficacy of an experimental manipulation intended for use in subsequent project. Following the collection of baseline ratings, 0 equals no anger, 10 equals extreme anger. Participants instructed to imagine a time in which they experienced feelings of intense anger. Completed 2-minute period of negative imagery before peak levels of anger. Before rating peak levels of anger. Okay, so they're just thinking about something sort of really angry and aggravating, and then rate peak levels of anger. Okay. Participants are then told to stop thinking about anger and instructed to imagine a time when they experience intense positive emotions. 20-second delay. Participants are instructed to rate levels of anger every 20 seconds for a period of 2 minutes. Increases in ratings from baseline to peak anger during negative imagery, and reductions in subjective anger from first to final rating are proposed as evidence of a successful manipulation. Okay, so what we're doing is we're having people come in, and we're saying what we want people to do is sit down, rate levels of anger, and then just really think about like an intense sort of angry memory. Okay, and so after they do that for 2 minutes. Then they rate their peak levels of anger. And then what we do once they do that, we say, okay, stop thinking about the angry thing, and now think about a time where you're sort of super happy. Okay. After you do that, what we're doing every 20 seconds, have them rate anger while they're thinking about their happy experience. And what we're hoping to see is increases in this pilot. We want to see increases from baseline to peak anger during the negative imagery, and reductions in subjective anger from the first to final positive imagery rating. Okay, so we want to say, if we've got this, if this is good manipulation, we're saying while you're thinking about the angry thing, we get you cranked up. And as you start to think about sort of positive things, from the first time you rate anger to the end after you think about positive things, we should see reductions. Okay, and so again, we're going to set this up. We're going to look at sort of want the null the null and alternatives, 95% confidence intervals for negative and periods of negative positive imagery, absolute magnitude of differences, tests, S values, base factor, and summarize everything together. Same thing we've been doing up to this point. Okay. All right. So pull up, if you would, the paired sample test data here. Okay. And your paired sample t-screening. Okay. I'm going to move you all over here. Minimize this. Okay, so if we're looking at our data set, we've got our participants, we've got our anger start, anger peak, and then subjective anger 1, 2, 3, 4, 5, 6. So this is anger start, anger peak. This is during the anger imagery. And then here, first start rating when they're thinking about positive stuff, positive stuff, positive stuff, positive, positive, down to the end of it. Okay. And again, what we want to see is an increase from here to here, and then a decrease from here to here. All right. People following along with what we're doing? Okay. So what we want to do is we want to start by screening these data. Okay. And so Erica, what is my primary unit of concern with these paired sample tests?
That someone didn't answer it.
Okay, yeah. So yeah, we're gonna go through and yeah, we've seen that we lost some ratings there for some folks, right? But first and foremost, when I'm screening, what's my unit of analysis in this paired sample test? Do you remember? What are we actually analyzing?
The difference.
Perfect. Do I have any difference scores in this set?
No.
Nope, I don't, right? So what I need to do is I need to calculate those difference scores. So what I'm going to do is I'm going to transform. You go down, I'm going to hit compute variable, okay? And I'm going to say, I'm going to create a new variable called angdiff, right? So anger difference. And what I'm going to do is I'm going to calculate anger difference as my peak anger score minus my initial anger score, okay? And what this is doing is I'm just taking sort of my time 2 rating minus my time 1 rating. Remember, I said wanted to do that because that just kind of puts things into perspective, or sort of makes that sign make some sense, okay? And then what I'm going to do is I'm going to hit paste. All right, and if I go here, what this is going to do, okay, say calculate difference score for calculate difference scores for anger screening, say, okay? And then if I go through and run this, we see down here what I've got is got my difference scores, okay? And I'm seeing a lot of positive difference scores. Natalie, what does this tell me?
That anger increase.
That I'm getting an increase in anger, right? If I would have subtracted my first anger score from my other anger score, I would have had a bunch of negative values, which would be fine. It's the opposite of what's going on, right? Which is fine as long as I interpret it correctly. But so this will help if you take your last assessment minus your first assessment. The sign on that will always be in the direction increase or decrease. It'll just help you out in terms of interpretations. Okay. Now I could go back up to transform and run through things again, or what I can do is I can just copy and paste that down. I'm going to create a new score called recovdiff, right? And what I want this here to equal is, I'm going to go sub anger 6 minus sub anger 1, okay? These are just my two variables here and here, okay? So go through and run this and run that, and now I've got my different scores. And again, Natalie, what are my scores at least for some of these variables, or for some of these scores? Or what's
increase? Is that what you're asking?
Yeah, so we've got some negatives in here. What does that negative? What does those negatives indicate?
A decrease.
Decrease in scores. Okay. So again, what we've got, and you have this in your handout here, what we're going to do for our screening is go through and calculate some difference scores. And what's important is because our paired sample t-test is just using these difference scores. Now, we're going to go through and say, sort of use X and Y and things like that in SPSS, but in the guts, in the background, all it's doing is SPSS just creating a column of different scores and running stuff on that, okay? So for our screening, what we have to do is create some scores that we can then go through, because this is where we're interested in terms of sort of distributions and outliers and things like that. Okay, people understand what we did here? All right. So what we're going to do here first is we do see we have some missing values, right? So I'm going to go through for the variables that I'm interested in. I'm going to anger start, anger peak. Okay, so I have full information there, right? And if I go down through and I take a look, these are 0 to 9 ratings, right? So that's all looking good. But if I go look at subanger 1, I see case number 18 has a missing value. Subanger 2, same thing. Oops. So I've got case 18 is missing values here, and case 18 is still missing values here, right? So because this person is missing values on this second analysis, what I'm going to do is I'm going to go File. I'm just going to say maybe working set. Okay.
What did you click on in File? I'm sorry, my computer screen's not so big.
Oh, no problem. I just File, Save As.
Okay, thank you.
Yeah. And then I'm saving this because I'm going to modify this data set, and I don't want to screw around with the original data. Because what I'm going to do is I'm going to say, hey, missing data for case number 18, and then I'm just going to nuke that guy. Okay. So once I've gone through and accounted for my missing data here, what we're going to do is we're going to go through, we're going to request skew and kurtosis and Z values or Z scores for my two different scores here. Okay. So I'm going to go to Analyze, Descriptives. You're going to go down, drop those over there. Options, skew kurtosis, save standardized values as variables. I'm going to paste that in. Okay. So here we can see in my syntax file, let's drop that in and say in distribution to different scores. I go through and run this. Here's my Z values. Here's my Z scores for these two things, right? So that's good. But if I want to go through and take a look at my outcome, all right. It's kind of low here, but all right. Allie, what am I seeing down here in my descriptives?
Looks like in terms of like phenotypic or just everything.
Yeah, just everything. What are you seeing?
So seeing for anger difference is the mean is about 4.45.
Okay. What's the min and the max telling me here?
That at minimum the difference is 0 and at maximum the difference is 8. Yeah, right. And so wanted to think about what does this mean within the context of my manipulation? Because this is a pilot, right? I want to see if this manipulation is useful. Right. I mean, it's showing that it is changing, or that it is manipulating.
Right, but not for everybody, right? It looks like some people are sort of reporting no change, right? Some people are reporting lots of change. On average, we see about a 4-point increase, which is probably reasonable, right? So just wanting to see and sort of identifying that, hey, at least in terms of this min and this max, at least some people, it's not universally, not everybody is increasing. There's at least some people, at least in this study, that's sort of not changing at all, right? Which is neither really here nor there, but it's just
good things that pop in the back of the mind, right? Like, okay, so this is kind of what's going on. And same thing if we're looking at your recovery. So this is where I have you rate your anger levels after I get you all worked up, and then have you think about positive stuff. What are you seeing here?
For the recovery?
Yeah.
That it's changing as well, or like there's some difference, but it's like kind of a wider range, I guess.
Mm-hmm. Right. And so I'm seeing for some people, I'm seeing decreases, but for some people at the max, I'm telling them to think about positive stuff. They're actually getting incrementally more angry about that, right? So I've got some variability here. What about the mean of my recovery diff?
It's smaller and also negative, but I guess that makes sense.
Yeah. What's easier to do, make people mad or get them unmad?
I get them mad.
Yeah, right. So again, this has nothing really to do with the screening of these data for our test, but it starts to become important in understanding, hey, what happened in my study? Like what's going on? Starts to give me some context with things. Okay. What about skew kurtosis? Allie, do you have any concern about that based on our indices here?
Not really.
Yeah, that's looking pretty good, right? Okay, cool. So we learned a little bit about our manipulation, right? In terms of what's going on, at least in our data, just by looking at the min and the max and the means. But from in terms of our distributions, looking like there's not too much going on there, at least based on that we are concerned about. Okay. And so, Riley, what do we want to do next? How about look at some graphs?
You read my mind.
Right, I know I did, right? I was just, you're just searching for words, right? All right, so we're going to go here. We're going to go analyze. We're going to go to descriptives. This time we're going to go through explore, okay? And explore is nice because what explore is going to do is it's just going to give us a shortcut for getting histograms and box plots. So if I go anger diff, recuv diff, go to plots, request histograms, turn off stem and leaf. Stem and leaves are nice, but we won't worry about those. And hit continue. And I'm going to take my participant number. I'm going to put label cases by down here. Remember that if we do this in our box plots, if we have extreme values, it'll label those extreme points based on participant number. If we don't, it'll label it based on position in our data set, which then we have to cross-reference and figure out. Can get confusing. So do we need to put anything in the factor list? Nope. We're not looking at different groups. It's just this one sample from time 1 to time 2. So you all go through and hit paste to make sure that it gets pasted in. I'm just going to hit OK here. Okay. So I always want to go through. We got full data for everybody. We got 42 people. That's looking good. This is just a lot of good descriptive statistics. We don't need to worry about it too much because what we're interested in looking at are these histograms. So anger diff. This is my increase in anger scores over the course of this anger imagery. Brittany, what are you seeing in terms of this histogram here?
It's like a really good normal distribution.
Ish, right?
Your ASPL, I mean, there's one, the value at the 8 is kind of off, but it seems to, I mean, it does pretty good.
Yeah.
You know, just like being evenly distributed. Except for that one, like, what, outlier, is that the right term?
Well, I wouldn't call it probably an outlier. I'd prefer extreme values to outliers. Our outlier has sort of certain connotation. But when we go through, we take a look here, it looks like either we've got a big spike at 8 or we're missing some folks at 7, but we don't have a huge sample, 42 people. So it looks reasonably sort of normal. And if I look at this histogram here, it looks like, you know, it looks generally effective what I'm doing, right? We've got at least well, based on this, it looks like probably one person who didn't change at all. Looks like maybe 6 people who sort of had a sort of small increase, but for the most part, we're getting stuff going on. So, Brittany, any concerns with that histogram in terms of distributional stuff?
Not to me, no.
No, I think it's looking okay. And you're on a roll. What about our box plot? What's happening here?
Well, your high value is 8, and then your low value is at 0, and then your median is about 4.
Yep. So once again, the interquartile range isn't perfectly symmetrical, but it's probably fine, right? So nothing too much going on right there. All right. Then if we look at our
question.
Yeah.
Sorry, going back to the first graph.
Yeah.
I'm following along on the Stata screening sheet, and it looks like there's different values for the y-axis.
Yeah.
Like
Yeah.
What is the, or why is that?
Well, that's because, and this is the problem. This is the limitation of histograms, is because Stata is creating a different histogram. In terms, it's binning things differently than SPSS does. And so, if you were to go through and change how things bin, the graph is going to change. It's going to look different. So you can start to sort of change how we go through and do stuff based on how many bins we get. Okay.
Okay, so it's still a measure of frequency,
Yeah, and this is why definite advantage of box plots, because the box plots, everything has a certain stuff. The midline is always going to be the median. The top of the whisker is always going to be your max or your highest value that's still within 1.5 times the interquartile range. Low whisker is either going to be the minimum or the lowest score within 1.5 times the interquartile range. This is a nice thing just because these box plots are going to be the same no matter what, or should be the same no matter what program you're using. Whereas with the histograms, you can start to get different looks depending on how you set it up. Does that help, Robert? Okay. All right. What about, well, help me out. Let's do this. Ari, what are you seeing with the histogram for anger recovery here?
I might be making the same mistake, but is that like a little outlier, like on the far
Okay.
right?
Well, I think this would be a good thing to identify, right? If you're looking at this, I would definitely say that it looks like there's one case that's separated away from the rest of the distribution, right? And what's going on with this case, Ari? What does this case represent? What is this person reporting?
Like high-end changes?
Yeah, right. So we had people start and be like, okay, tell me your anger rating. Now I want you to think about something nice. And at the end of it, after they've made a bunch of these, then they're ready. What is this person doing?
They're still feeling angry.
Yeah, not just still feeling angry. They've increased their anger, right? But is that typical of the sample? No. Okay. So, and this is starting to get to be a high value. In the grand scheme of things, is this value likely to start pulling this mean around a whole lot? Probably not, but it's definitely worth noting that at least one person in this sample is reporting increases in anger. And so this might be a key to me if I'm a researcher to go through and see what was going on with this person. Okay, we're seeing sort of most people reporting no change. That's the modal response to my manipulation, which is not great. If my modal response to my manipulation that's intended to reduce changes that people don't. But we've got some negative skew here, right? So I don't know that I'm sort of going to write this off, but it's looking sort of like this was maybe less effective than my first manipulation, right? And then down here, Ari, what are we seeing in terms of my box and whisker plot here?
The upper part is a little bit above 2.5, and then the lower is 2.9.
a little bit below negative 7.5, and your middle is like 0.5, I'd say.
Yeah. Okay. This is probably 1 because these have to be whole numbers and things like that, right? But remember, this is my median. This is my first quartile, my third quartile, and so on and so forth there. Okay. So based on this, do we have any concerns about the underlying assumptions of my test? Probably not. Okay. Natalie, what's the last thing I want to check though?
Like in terms of the graphs or in terms of?
In terms of sort of finish up my screening here.
The standard error.
Okay, standardized scores. Standard error, yeah, right. So look at my z-scores, right? Basically, based on my plots, I already know what I'm going to find. I'm not going to find anything I'm too worried about, right? But what I do want to do is I want to go through and take a look and say, okay, I want to look at my descriptive statistics for my z-scores to just kind of see kind of what the range are, right? And so if I go through and what I'm going to do is I'm just going to copy this, okay? And if I just change, because when SPSS calculates z-scores, it just takes your variable name and just adds z to the front, okay? And get rid of save, because this is the command that gets rid of that saves things as standardized scores, so I'll get rid of that. I don't need skew and kurtosis, so get rid of that, and I'm back down to just getting my descriptive statistics for my z-scores. Or I could go analyze descriptives, right? Get rid of those, add these two. I can go options, take my skew and kurtosis off, continue, turn off standardized, and paste. And it gives me the same thing. But again, just showing that sort of once you start to get a feel for this syntax, it's just a little bit easier to go through and run it like this. Okay. So if I go through and I do that, run my descriptives. All right. And Rachel, can you tell me what I'm seeing here in this descriptives table?
Yeah, it looks like it ranges from, I forget what the z-scores are. Are those standard deviations?
Yep.
Or not standard, yeah.
Yep.
2 standard deviations below and around 2, but 1.6 as the max.
Mm-hmm.
And then a little bit larger range for the...
Yeah. Anything here that would cause us to be concerned? Okay.
No.
Yeah. So again, when we're going through and looking at these z-scores are just a way to sort of formalize and communicate how far or sort of the level of distance these scores are from a relative mean. Looking at these graphs, I already know that there's nothing going to be problematic, but it's easier to go through if I can give people individual scores to communicate that this is sort of the relative min and max in standard deviation units, or given my sample size, but here everything's looking to be okay. All right. So if I go through and wanted to talk about this standard deviation, or screening for my paired sample test, is pretty easy. It's just same sort of stuff that we would do with a single sample test. So we'd say case number 18, missing values for subanger 1 to subanger 6. So we would say no evidence of problematic values. So case with missing value moved 42 people in my reduced set, right? Talking about my distributions for anger difference, recovery difference, right? Just kind of going through, giving my statistics for skew and kurtosis, just giving a little bit of a visual description of my histograms and box plots, talking about extreme values, everything's looking out here, and then recommendation, aside from a single case, little evidence of violations, So we're good to go. So quick and easy, no big deal here. Questions about the screening for this paired sample test? All right, cool. Let's do this. Let's take 10. We'll come back to take a quick break and then finish up with our tests and sort of round out this last piece of things. Okay, so come back at 4:35. All right, folks. Last push. How are we feeling about screening? Sort of people starting to get the rhythm of sort of this procedure in terms of how we're doing data, going through, taking a look at stuff. Thumbs up, ish. Thumbs sideways. Okay. This will, as you start to work through. Anybody show of hands? Anybody started working on this t-test problem set? Brittany's done a little bit. Okay. This one will be challenging. All right. There's going to be a lot of stuff to go through and address. So just make sure that you're getting on it early, thinking carefully about this. And if you have any questions, let me know. Okay. So to work together, but if there's concerns about how to go through and craft some or how we go through and describe things or sort of present anything, make sure to let CJ or I know. Okay. All right. Cool. So we will go back. So we've got our screenings done. Not too bad for our paired sample test, but we've decided that things are pretty good. So what we're going to do is now we're going to go through and run our test. So we're going to go to Analyze, Compare Means. Now we're going to go down to Paired Sample Tests. Okay, I'm going to pick that. And then what SPSS is going to ask you to do is it's going to ask you to start pairing things. So for my first, right, I'm going to take peak anger and put it as variable 1, initial anger, variable 2. And then what I'm going to do is here, I'm going to take my last anger recovery score as variable 1, make anger recovery 1, sort of my variable 2, okay? And that's all we need to do. Right? Go through and hit paste. Take a look at your syntax file. Pretty straightforward. Peak anger or anger peak, sub anger 6 with anger start, sub anger 1. Go through, run this, and this is what we get in terms of our outcome. Again, we get our descriptive statistics where we get at peak and initial, recovery 6, recovery 1, making sure that all of this looks good, kind of consistent with what we would expect based on our screening. Here, it's giving us the correlation between our two assessment points. We see that our anger imagery scores are correlated to what seems to be a lesser degree than my recovery scores. Okay, this is going to be have a direct relation to the power of your test. Variables, paired measurements that are correlated to higher are going to result in more powerful tests than paired correlations that are or paired measurements that are correlated lower, right? So it looks like more consistent recovery scores than peak anger scores, but you don't need to worry about that too much. Down here, going to take a look at our paired sample tests. And Natalie, what are we seeing in terms of our paired sample tests down here?
Well, the mean for peak anger and initial anger is higher than the second pair. Did that make sense?
Okay, yeah. So, but if we're going down through, so yeah, we've got our paired statistics and our paired samples. What about if we go down through and take a look at our paired samples tests down here? What are these telling us?
Do you want me to talk about like the confidence interval?
Sure. Yeah.
I guess I'm not sure about
Yeah. Just,
I guess the confidence interval for the difference between peak anger and initial anger, they're both positive, but it's a pretty like narrow-ish confidence interval.
Yeah, not too bad.
And the same goes for the second pair.
Okay, right. And so we've got, I mean, a size of 42 still probably isn't large, but it's sort of bigger than some of the other things that we've done, right? Natalie, can you give me for peak anger, can you give me or for the anger imagery, can you give me an interpretation of that confidence bound, of those confidence bounds?
I'll try my best. So expected values for the difference of peak anger and initial anger likely fall between 3.795 and 5.11.
Mm-hmm. Right. And so from a practical standpoint, if let's say, so Erica, this is my student Adam had taken it from one of his things, but he had talked with Ben about, because Ben, Erica's advisor, has done anger related stuff. And so, okay, so is this, how do we manipulate anger, sort of trigger anger within the context of an experimental setting, right? So I could say, hey, this anger imagery paradigm that I've used for people coming in, I would say sort of looks like on this 0 to 9 scale, I'm getting an average of about 4.5 points. That's about half the scale. That's pretty good movement on stuff, right? But I don't know. That was just this sample. Sample would say that anywhere from about a 3.8 to a 5.1 unit increase in anger is about what we would expect in the larger population. Okay, 4.5 is still my best guess based on the data that I have, but anything falling between these bounds would be pretty reasonable, right? So, Erica, if you were doing anger research, how would you feel about this manipulation?
Fairly good.
Yeah, fairly good. Looks like it's doing okay, right? And Natalie, so good job with the confidence interval. What about our test statistic? What are we seeing there?
I guess the test statistic for the first pair is much larger than the second pair.
Yeah, it's massive, right? Huge. A T statistic of 13.68. That's incredibly large, right? And if I go through and that's 7.12 times 10 to the negative 17th. How much evidence do we have, sort of based on these data, what's the strength of evidence we have for that, for the difference between sort of pre and post in anger ratings is not 0?
Pretty strong.
Yeah, really strong. Like basically, functionally, if in the actual population, having people sit down, rate their anger scores, and then having think about negative anger stuff or negative imagery, and then rating their anger scores afterwards, if the true population value for that is 0, these data functionally can't exist, right? So really, really compelling, sort of overwhelming, compelling evidence for that. What about for our recovery, right? Because we were worried about that. We saw less movement in terms of recovery. Based on our tests, what can we say here?
It's not as strong, but it's kind of compelling.
Yeah, right. I would still say that p-value, again, if we're thinking about p as a continuous strength of evidence, I'd be confident about this happening, seeing some non-zero reductions all day long. Okay, and so it's still very, very strong evidence here. But what about my confidence bounds? Can you? And then I'll leave you alone. Just tell me what's going on with this.
For both of them, or for
no, just for the recovery here.
So the likely recovery scores are between those two values, essentially meaning that they're like the average distance is likely, or not distance, difference is likely to fall like on the negative side, which means that there was probably like a decrease in anger.
Mm-hmm. Yeah. But here we're saying sort of, I'm looking at this confidence bound, I'm saying sort of based on the data that I've collected, it looks like about sort of having people, once I get people worked up, having people think about positive events sort of over the course of, say, a 2-minute period, I'm getting about a little over a 1.5 point decrease in anger. But my confidence bound says that anywhere from about a 1 point decrease to a 2.3 decrease is probably what we can expect, sort of based on the data that we've collected here, right? So overall, how does this match up with the anger activation sort of piece of things? Yeah, I said I'd leave you alone, but that was a lie. I lie sometimes. It's like it's like when your coach says, like, just one more line, and then you're done. That's never the truth. That guy will lie to you every day. Yeah. So what do you just conclusions? What would you take from the extent to which this manipulation works?
I'd say it works fairly well. I mean, especially for the difference of peak anger and initial anger, but also the recovery method seems to be
doing something at least, right? Is we have pretty clear evidence that it's not zero, right? But the extent to which this is practically meaningful, I don't know. We'd have to go through and take a look, right? So if we go through and pull you back in here. So again, SPSS, this is just what we went through, going through and how we get that paired sample test. Here's our output that we just went through. In Stata, pretty easy, straightforward. We just say t-test variable sort of post-test equals pre-test, t-test subanger 6 equals subanger 1. It's easy. This just pops out and we get all the same stuff that we did before. So that's pretty easy peasy. In terms of write-up, okay? Again, this piece is just kind of talking about, just telling me what we did, just making sure that we clarify on sort of the goals of things. This is screening. You don't have to worry about that because I'm going to have you screen another thing. So you'll already have that piece kind of put together. But then here, in terms of our interpretation, scores collected in the pilot provide strong evidence against models specifying 0 difference in ratings of subjective anger during negative and positive imagery, right? And I just throw in all my statistics here. Just kind of put them in, right? We're just saying there's very strong evidence, right? If we go through and calculate our p-value here, you see we're using scientific notation. Again, because if we say p equals 0.001 versus p equals 7.12 times 10 to the negative 17th, that's orders of magnitude difference in terms of strength, right? And so I would argue that it's helpful to try and go through and communicate this in some way. S values for this, 54 heads in a row, right? That's not going to happen. Even for our lower effect, 16 heads in a row, that's suspicious, right? Our Bayes factor for both cases are very, very large, right? So here we're saying the 4.5 unit increase in subjective anger following negative imagery task consistent with a 2 2/3 standard deviation increase in ratings relative to variability at baseline, okay? And we see here for my effect size calculated glasses delta, right? Robert, why does glasses delta make sense with this design?
Of the small sample size?
Not because of small sample size. And my sample size here isn't too bad. 40-some people for a paired sample test is going to be pretty powerful. Why does glasses delta make sense for this?
Well, because we are interested in the change score, so the baseline would be the best measure of standard deviation.
I've got a nice baseline. So the variability of anger at baseline, right? Some people are going to come in angrier than other people, but it's just a nice, meaningful metric for this test, right? So we've got here, so we say data compatible with increases anger ranging from 3.8 to 5.1 units in the hypothetical population respondents completing manipulation. It's important to note the lower bound estimate provided by this interval continues to support over a 2 standard deviation increase in anger ratings relative to baseline. So we're saying that this is sort of pretty big, right? Point estimate anger recovery for positive imagery, more modest, right? But remain consistent with conventional benchmarks for a medium-sized effect. That should be delta, not D, okay? Talking about my confidence interval, Results provide clear support for observable change in subjective anger following both manipulations, although imagery appears to have a stronger influence on subjective experience than positive imagery. So you're just kind of tying all this stuff together in terms of, and sort of presenting it in something that's going to tell people exactly what's going on, interesting information in terms of practical effects, strength of evidence, expected values in population, right? Because what we don't want to do is, if this is, again, Erica's study, right? And then Ari comes in, she's like, oh, I'm going to use Erica's manipulation, and I go through and I find that I didn't get a 4.5 increase in subjective anger. My increase in anger was, that I saw in my sample was, just a little, sort of just under, so 3, let's say 3.5 points. Okay. Well, that's still probably pretty close. Your confidence interval and Erica's confidence interval are going to overlap quite a bit, right? So we would say that probably there's not something completely different going on. So just trying to give people an idea for what they might expect based on the data that you've collected. So here's just a sort of shorter write-up, how you might present this in a publication. Okay. So just want to finish up in terms of thinking about strengths and limitations. All right. Again, for our paired sample tests, a lot of the stuff that we're looking at fits really nicely into these paired sample tests. It's a more effective and efficient use of our resources, but the biggest thing is, because we get reduced variability, because I'm measuring everybody at the start, and then I'm measuring everybody after, right? And all the individual differences in terms of how you're feeling, how you respond to things in general, all that's being taken into account. You're essentially your own control person. And so because we're looking at this difference in change, as opposed to variability across individuals, what we end up with is a far more powerful analysis, okay? Far more powerful analyses. And this starts to become important for thinking about theses, dissertations, projects, and stuff like that that you might be developing. We, in psychology, are chronically underpowered, with the exception of repeated measure stuff. These are just super powerful tests. If there is a way to go through and incorporate a repeated measures design in any studies that you're doing, would strongly encourage you to do it, because you're much more likely to detect these effects, even if they're quite slight. Okay? But the limitations, right? If I've got time-related factors, right? If I've got carryover effects, right? Where, hey, if I do this now, things are going to be different later on, and it's not going to be an apples-to-apples comparison. These types of things can come on. Practice effects, right? If I'm looking at performance on something, right? And let's say, Ari, you're looking at performance on a spatial awareness task. But if you give someone it first time, they kind of learn something from it. And if we see increases in the second time, it's hard to know if it's because of something you did or because they just got better at doing it, right? So we want to be careful there. Order effects, right? So this is why it's hard to do like a repeated measures design of, let's say, in clinical work, right? Well, I'm going to have you do CBT, and then I'm going to have you do psychodynamic treatment or something like that. Well, I can't tell you to forget all the stuff that I just taught you. Like, that's going to be there. And now that's contaminated my second assessment, because all that stuff is there to begin with. And so these are the types of things that we really are hard to go through and put together with a repeated assessment. But if we can do it, in the words of Zach Williamson, repeated measures are pretty damn slick, okay? Super powerful, a really nice way to go through and put things together. And so if you can use them, super, super beneficial for this, okay? So summary, we got our single sample test, right? A single sample t-test, we're looking at the mean of some continuous variable compared to some known reference population when I don't know the population standard deviation. If I do know the population standard deviation, or the population variance, what can I use? What's the other test that I can use instead of a single sample t if I know the population variance? What do we start out this whole thing with?
Since I'm going to just guess and say z-score.
Yeah, you're exactly right. It's just a z-test, right? If I know what the population mean and standard deviation is, I don't just use a z. I don't have to worry about t, right? But we rarely are in situations where we have where the population variance is known. Okay, and so in this situation, then we're working at these single sample t-tests. Independent sample t, this is where we're looking at continuous outcomes across two different independent samples. We've got two different populations that we want to compare. Got a sample from one population, got a sample from the other population. Going to see, do we have evidence of some non-zero difference? Now remember that our null hypothesis test will give us an indicator of the extent to which these data are compatible with the null hypothesis, but it's not going to tell us whether it's meaningful or important. That's something that we have to come up with on our own, right? And again, Brittany, this is where I'm trying to encourage you guys to move off, or you all to move off of using, oh, it's significant, it's not significant. I don't know. Anybody can see whether or not something's above or below 0.05. That's not useful, right? And significance gets confused with important. And even the stuff that is sort of right at that 0.05 level isn't overly strong and compelling arguments for an effect to be popping up. And so what we want to do is talk about things in terms of strength of evidence. Do we see some evidence of differences? And that's a different question than whether or not that difference that we're seeing is meaningful, sort of depending on our confidence bounds. So just trying to use this flexibly. Then finishing up with our paired sample T. This is looking at, again, a continuous outcome collected on two different occasions in the same group of individuals. Or remember that we can use this for our matched sample or our matched designs. We don't see a lot of matched. I don't know. Does anybody see a lot of matches? We don't see a lot of matched designs in clinical. I mean, do people in experimental use matched designs? It's kind of an old school kind of classic way to try and reduce variability in my set by pairing people up on some sort of important characteristic. But traditionally, we can go through and use this paired sample procedures with a matched sample. So that's the one sort of difference thing, as opposed to just having one and going, just having one group and measuring on multiple occasions.
Is it any different? Because I'm looking at the problem set. Even though it's not popular, I'm seeing a matched pair. You do the same thing?
Oh, I might. You've got a good eye, so think about that. Yeah. All right. So again, the null hypothesis with our paired test is that the mean of the different scores in some population is going to be equal to 0. Okay. So remembering that for our paired sample T, all it is a single sample t-test on our different scores. So again, if I go analyze, compare means, paired sample T for, let's say, just our peak anger stuff, okay, and I hit OK, and then if I go analyze, compare means one sample t-test, and I do a one sample t for my anger diff, okay, with a reference value equal to 0. Okay. See, for my paired sample test, my test statistic is 13.60. For my one sample test, 13.68, or excuse me, 13.680, 13.680. Degrees of freedom are the same. P-values, 7.12 to the negative 17th. Same thing here, right? It's the same test, right? Here, I just set it up as a classic paired sample t-test, and what SPSS did is it created different scores and then ran a single sample test with a 0, or because I already did it, I can just set it up as a one sample test with a reference value of 0. It gives me the exact same thing. My confidence bounds are identical, okay? It's all the same, right? So that's the one thing you want to remember with your paired sample T. It's not magical. We're just going through and we're looking at a column of different scores and sort of using that as our inputs, as opposed to sort of necessarily what's going on at time 1 and time 2. All right, so we got some syntax, but you've already got that in your handouts. So, all right. Took us a while to get through means or t-tests are, but I think that's fine. This is going to be kind of the basis for everything else that we do in terms of means-based tests moving forward. If we've got a good handle on this, we're going to be in pretty good shape. How are you all feeling in terms of got a headspace for t-tests, sort of different types, sort of different considerations and things? Okay, cool. So go through, and again, our next set won't be due obviously this Friday, but it will be due the following Friday. This is going to be a big one. This is probably, there's a lot going on in this. So just get going early, work together. Let me know if you have any questions. But otherwise, you guys are doing really well. Again, nice work on problem set 3. Take a close look at that. Make sure that you're square on any comments or feedback on that. And then just let me know. Okay. All right, folks. Thanks. Have a good evening. Thanks for hanging in there. And we'll catch you on Wednesday. All right. We'll see ya.